I suggest we start from the file with equations. Each file with equations will have the same structure. There are three if statements: if get values, if run algebra, and if run dxdt. If get values, this is where all the numerical parameters can be accessed, as well as all the values of inputs and state variables, as well as delays. If there are delays, naturally this simple example is non-delayed. If run algebra is empty for this very simple example. However, you will see later that for more elaborate systems, it becomes interesting to do some of the algebra here instead of directly in the dxdt vector for clarity, as well as when outputs have to be defined. We will see a particular example where the run algebra if statement is used. In any case, the if run dxdt if statement is where the dxdt vector is defined. So comparing with the differential equations here, we see that the differential equations of the RLC circuit are exactly the same as those implemented here. The advantage of accessing numerical values of parameters from the param structure is that you do not need to have numerical values inside the analytical equations, and you will be able to change all numerical values from the data file where the parameter structure is defined. This avoids mixing up equations and values of parameters. So this is a good moment to see how the parameter structure is defined. All the numerical values are written in this data file. Naturally, here is you'll have a lot of flexibility as a user. You can write this set of data in any way you want. What is important is that a number of structures have to be written. The DSA structure is the main structure of the complete toolbox. It stands naturally for the DSAnalysis toolbox. And in this particular data file, we write the data structure. And there are substructures to this data structure, in particular the param structure, which is the one from which you will be able to call parameters such as circuit parameters, control parameters if there are any, as well as input parameters. The base structure is optional, but I recommend using one in such a way that you can keep track of the scaling you use, whether you work with a per unit system or not. I personally write a base structure so I can keep track of the scaling parameters. And naturally, the F1 is the value of the fundamental frequency. In this particular example, I have defined F1 as 1 Hertz. As far as the parameters are concerned, for this very simple example, we have 3 parameters: the resistance, the inductance, and the capacitance. I have transformed these parameters into their per unit equivalent before putting them in the parameter or param structure. And naturally, in the equations file, I call the very same parameter structure to retrieve those values. For delayed systems, there will be an additional structure inside the data structure, and we will get to it when considering a delayed system. So in addition to the equations, the if get values if statement is where you can access the values of inputs and state variables. Those are listed as well in the variables file. So there are essentially 2 types of cells to define in this file. The LASI stands for large signal variables, and the SMSI stands for small signal variables. When working on the calculation of periodic trajectories, we consider naturally the large signal variables, and I will get to the small signal variables later on. For our simple example, we have only one input variable, which is the voltage at the source, Vs. We have only two states, the inductor current, IL, and the capacitor voltage, Vc. We could define any number of outputs. We could, for instance, take both state variables as outputs. Here, I have only considered the inductor current as output. Naturally, the two delay variables and the delayed variables are left empty, as the system here does not have any delays.